Most engineering teams can wire up an AI retrieval pipeline in an afternoon, but proving the new version actually works, that it is measurably better than the one deployed last week, takes a completely different set of skills. The standard industry workflow relies on raw point estimates. An engineer runs a new prompt against 50 hand-picked examples, spots an uptick in the aggregate score, and pushes to production. Relying on spreadsheet vibes like this is exactly how silent regressions reach production. Your monitoring system stays green, your aggregate accuracy looks stable, but your model is failing on a critical edge case nobody thought to measure. We have to treat AI evaluation as a strict systems engineering discipline. Knowing the formula for F1 or accuracy is table stakes. The real work is designing a system that can reliably detect a failure before it ships. A true evaluation system requires exactly two components: a calibrated measurement instrument and a rigid, pre-agreed decision rule that maps that measurement to an action. If you have an instrument without a decision rule, you don't have an evaluation system. You have a dashboard displaying useless numbers. We are going to architect a production-grade release gate from first principles, stripping away the noise to build a system you can actually trust. Until teams stop relying on raw point estimates and start engineering statistical gates, every merged pull request is just a coin flip with extra steps. Let's start with the foundational architecture. You have a system under test, outputting to a metric, but that metric block hides a gap. There is the construct, the abstract property you care about, and the operationalization, the concrete code you write to measure it. If your operationalization is just counting grammatical errors, you haven't built a helpfulness metric. You've built a grammar meter. The precision of your math is completely irrelevant if you are measuring the wrong construct. This brings us to criterion validity. This is the ultimate test of whether an offline metric actually connects to reality, or if it's just a number going up in a vacuum. This scatterplot shows the methodology. Score 200 real production logs against your offline metric. If it separates successes from failures, it's valid. But if the area under the curve drops near 0.55, your offline metric predicts failure at the exact rate of chance. Teams will routinely spend entire quarters optimizing a metric without ever checking if it maps to a business outcome. Any offline metric that cannot statistically predict a real-world failure is an illusion. Delete it immediately. Once you know you're measuring the right construct, the next architectural requirement is reliability. We have to bound the metric with a known noise floor. Generative systems are inherently non-deterministic. If you measure the same system twice, you will get two slightly different answers. Even if you pin your temperature to 0, you cannot escape variance. Hardware load balancing, floating point non-associativity, and silent provider updates all introduce run-to-run variations. Your evaluation judge is also a generative model, which means it carries its own variance. Minor tweaks to a prompt will alter the judge's output, shifting your final score. You handle this with a mandatory engineering procedure. Run your exact evaluation suite twice against an entirely unchanged system and record the difference. This chart shows the result. The fluctuation between 81 and 83% is your noise floor. We enforce a strict rule. Improvements must be larger than this noise floor. If a score goes up 0.5%, but noise is 2, you haven't improved. Publishing this noise floor right next to the core metric is the single most critical and most frequently omitted element in modern engineering dashboards. Without explicitly measuring the instrument's variance, your team will waste hours arguing over deploy decisions driven entirely by system noise. We have our noise floor. Now we need to move past raw scores and start calculating population estimates. The trap of the point estimate is thinking the raw score matters. We don't actually care what a model scored on 100 specific test items. We care what it will score on the millions of real-world interactions those items represent. To translate a point estimate into a true population range, every single score in your pipeline must carry a confidence interval. The technical hurdle here is that nonlinear metrics do not have simple, closed-form standard errors. You can't just plug them into a basic formula. To solve this, we use the Bootstrap BCA method. We take our pool of test items and rapidly resample them thousands of times. By recomputing the metric on each resample, we generate a highly accurate, bias-corrected confidence interval using a single code path. But there is a strict constraint for clustered data. If your 400 test cases are drawn from only 40 user sessions, treating them as 400 independent variables will produce an artificially narrow, deceptive interval. To fix that, you must use a cluster bootstrap. You resample at the session level, keeping each conversation's items together to maintain the mathematical integrity of the test. An aggregate score without a corresponding confidence interval isn't a measurement, it is a rumor. Now we have to address dataset design and suite sizing, because an interval is only useful if your test has the power to detect a change in the first place. This is dictated by the minimum detectable effect, or MDE. It defines the absolute smallest true improvement a suite can mathematically detect. Overlapping curves show why small datasets fail. A 3-point regression becomes indistinguishable from noise. In an unpaired test, item difficulty eats your statistical power. We fix this through paired testing. By running both models on the exact same inputs, we connect identical test items. Because the item-level variance is shared between the two systems, pairing strips that variance away completely, isolating the pure performance delta between the models. Applying a paired statistical test, like McNemar for binary outcomes, drastically reduces the sample size you need to hit your minimum detectable effect. You must calculate your MDE before you ever execute the evaluation suite. You size the test to answer the question, not the other way around. Deploying an underpowered suite is actively worse than having no suite at all, because it provides a false green light to failing code. We can now assemble the complete architecture. Your golden dataset feeds the system under test. That generates a metric. We bound it with a noise floor, process it through inference, and feed the result into our final block, the decision rule. The decision rule maps your population estimate, its interval, and a pre-agreed threshold directly onto an automated action. The outcome is strictly binary. The pipeline automatically holds the deployment, or it automatically ships. Human vibe checks are removed from the loop. We also have to acknowledge the financial reality of this architecture. Evaluation compute is not free. Running an LLM as a judge on every single commit is a massive line item for any engineering department. And the hidden cost of maintaining that golden dataset requires constant human annotation and strict version control. Which brings us to the rule of deletion. If a calculated metric does not have the statistical power to change a ship or hold decision, delete it. Save the compute. We've moved from a naive spreadsheet of raw scores to a valid, reliable, statistically powered production gate. Closing the gap between building an AA system and proving it works requires this level of absolute rigor. Everything else is just decoration.